this exercise, we're trying to construct the OLS estimator to estimate a relationship between y as our dependent variable and x as our explanatory variable, but there's a twist. And the twist is that we're trying to impose that the intercept of our fitted line, the beta naught hat, is equal to 4. So we're making this as a restriction on our line. And the fitted line that we choose might look something like this. The only restriction that we've placed on it is that the intercept is equal to 4. Now we're going to construct the OLS estimator in exactly the same way as we have done in the past. The equation of our fitted line is y hat is equal to 4, that's our imposed intercept, plus beta 1 hat times by the observation of x. So we're trying to choose the line that minimizes the sum of squares of the fitted residuals. And remember, the ui hat is just equal to the observed value of y minus the fitted value of y, but we know that the equation for the fitted value of y is equal to 4 plus beta 1 hat x, so our fitted residuals are going to be equal to yi minus 4 plus beta 1 hat xi, or this is going to be equal to yi minus 4 minus beta 1 hat xi. So we're trying to construct our estimator such that we minimize the sum of squares of these ui hats. And that's going to be the same as minimizing the sum of squares of yi minus 4 minus beta 1 hat xi. Now, in order to minimize the sum of squares of the residuals, we're going to need to differentiate with relation to the thing that we're choosing. And the only thing that we're choosing here is that beta 1 hat. So we're going to differentiate our expression with relation to the thing that we're choosing. In other words, we're differentiating with relation to beta 1 hat. Now we've seen that when we're differentiating this summation, we can treat it as if we're using the chain rule, in that we can bring the 2 down the front, we lower the power by 1, so that power will become 1 here, and then we multiply by the derivative of what's inside the brackets. So we can rewrite this derivative as being equal to 2 times by the sum from I is equal to 1 to n of yi minus 4 minus beta 1 hat xi, and then we multiply by the derivative of what's inside the brackets with relation to beta 1 hat. The derivative of yi is 0, the derivative of minus 4 is 0, the derivative of minus beta 1 hat xi is going to be equal to minus xi. And then, because we're trying to find the minimum, we set that all equal to 0. So we can rewrite this derivative, or this first order condition, as minus 2 times by the sum from I is equal to 1 to n of yi minus 4 minus beta 1 hat xi, all multiplied by xi, is going to be equal to 0. Now we can simplify this a little by dividing left and right by minus 2. And that just leaves us with the sum of the yi minus 4 minus beta 1 hat xi, all multiplied by xi, is going to be equal to 0. Now we can split this summation into 2 parts. So let's rewrite that as the sum of yi minus 4 times by xi minus beta 1 hat times by the sum of the x squared. And what we've done here is we've split this into 2 parts, one part relating to the beta 1 hat, one part relating to everything else. And this is going to be equal to 0. So now we can add beta 1 hat times by the sum of x squared to both the left and the right, giving us that the sum from I is equal to 1 to n of yi minus 4 times by xi is equal to beta 1 hat times by the sum of the x squared. In the final step, we can divide left and right by this sum of the x squared, giving us that our estimator for the slope parameter is equal to the sum between I is equal to 1 to n of yi minus 4 times by xi all over the sum of the x squared. Now this might look familiar to you in that, if you remember, when we estimated the relationship yi is equal to beta xi plus ui, in other words, we imposed that the intercept was equal to 0, we had that our estimator beta hat was equal to the sum of the yi xi over the sum of the x squared. Now the estimator that we've got here, beta 1 hat, looks very similar to this one. The only difference is that yi is replaced with yi minus 4.